Is the universe infinite? People ask me this all the time, and the answer is tricky. It needs some thought. The answer depends on things we don't know for certain yet. How much matter? How strong gravity? But the possibilities are far stranger than you might expect. Right now, space is expanding. Galaxies racing away, thousands of miles per second. Run time backward. Everything gets closer, packed tighter, keep going. Everything compressed into something unimaginably small. That moment, we call it the Big Bang. About 13.8 billion years ago. What happens next? Three possibilities. Three ways this could end. 1. Expansion forever. Stars burn out one by one. In 100 trillion years, the last star dies. Civilizations huddle around dying embers, then darkness forever. 2. Perfectly balanced. Same expansion, same ending. 3. Gravity too strong. Everything falls back together. Maybe 50 billion years from now, crushed back into a single point. Which fate is ours? We don't know yet. Let me show you what we do know. Right now, as you're reading this, space is expanding. Galaxies racing away from us. Not just drifting, racing. Thousands of miles per second. Tens of thousands, some even faster. Space itself is stretching, pulling galaxies apart like dots on an inflating balloon. Run time backward. Imagine hitting rewind on the universe. Everything gets closer. Galaxies pack tighter together. Keep going, further back. Everything in the observable universe compressed into a space smaller than this room. Keep going. Smaller than a marble. Smaller than an atom. Unimaginably small, unimaginably dense, infinitely hot. That moment, that beginning, we call it the Big Bang. Not an explosion in space. There was no space yet. The explosion of space itself. Space and time began together. Everything we can see, everything we can measure, everything we call the universe emerged from that moment. About 13.8 billion years ago. How do we know this? How did we figure it out? In the 1920s, astronomers noticed something strange. Edwin Hubble and others measured light from distant galaxies. The light was redshifted. Wavelengths stretched out toward the red end of the spectrum. The farther away the galaxy, the more redshift. That's the pattern. And patterns mean something. Motion stretches wavelength. You've heard this with sound. A car approaching you, the engine sounds high-pitched. As it passes and moves away, the pitch drops. Lower. That's the Doppler effect. Sound waves get compressed approaching you, stretched when receding. Light does the same thing. The redshift proves it. Galaxies are moving away. Not through space. Space itself is expanding, carrying the galaxies with it. Measurable, repeatable, undeniable. So space is expanding. What happens next? What happens next? Does the universe expand forever? Or does something else happen? The answer depends on a balance. How fast is space expanding versus how hard is gravity pulling back? Think of it like throwing a ball upward. The ball rises, but gravity pulls it back down. Whether it comes back depends on how fast you threw it. Throw it slowly. Gravity wins. The ball rises, slows, stops, falls back. Throw it faster. At a critical speed, escape velocity, the ball just barely escapes. Keeps rising forever, but its speed approaches zero. Throw it even faster. It escapes easily, keeps rising, never comes back. The universe is the same. Everything depends on the balance. How fast is space expanding versus how hard is gravity pulling back? And that gives us three possibilities. Three ways the story could end. Fate 1. Expands forever. The first possibility is this: space expands too fast. Gravity can't slow it enough. The universe expands forever. Galaxies race apart. Eventually, they're so far that light from one galaxy can never reach another. Each becomes isolated, alone in an ocean of darkness. Stars burn out one by one. Everything goes cold, dark, empty. The universe doesn't end in drama. It just fades, gets colder and colder, more and more empty, until nothing interesting can ever happen again. Forever, for humanity, stars die one by one. In 100 trillion years, that's 100 trillion years from now, the last star burns out. Civilizations, if any remain, huddle around dying embers, extracting the last bits of energy from cooling stellar cores. Then darkness, forever. No new stars can form. No energy left anywhere. Just cold, dead matter drifting apart through infinite black space. Nothing interesting can ever happen again. Not in a billion years. Not in a trillion. Never. Fate 2. Critical speed, flat universe. The second possibility is this: space expands at exactly the critical speed. Gravity pulls back just hard enough to slow the expansion, but not stop it. The universe keeps expanding forever, but slower and slower. At infinite time, the expansion rate approaches zero, perfectly balanced on a knife edge. This is the flat universe, and its fate is similar to the first case: expansion forever, but balanced precisely at the critical rate. For humanity, we'd never know the difference from Fate 1. Same expansion, same timeline. The universe gives us trillions of wires either way. Stars still burn out. Same cold ending. We just know the geometry is flat. Fate 3. Big crunch. The third possibility is this: space doesn't expand fast enough. Gravity is too strong. The expansion slows, then stops, then reverses. Galaxies stop receding, then start approaching. Space begins contracting. Everything gets closer together, denser, hotter. Think of the Big Bang in reverse. Galaxies collide, merge, stars are ripped apart. Matter gets compressed, temperature rises. Eventually, space contracts so much that atoms can't exist. Then molecules, then even subatomic particles. Everything collapses back into a single point, a big crunch, the opposite of the Big Bang. The universe that began in fire ends in fire. For humanity, galaxies start rushing back together. The sky fills with light as everything compresses. When? Maybe 50 billion years from now? Maybe less. We don't know. Everything we know crushed back into a single point. Does it bounce? Start again? Create a new universe? We don't know. Which fate is ours? In the mid-1960s, we didn't know. The answer depends on how much matter exists, how strong gravity really is. Not just the matter we can see, stars, galaxies, gas, but everything, including matter we can't see directly. We're still measuring. We're still trying to figure it out. And while I was thinking about this, about the universe expanding or contracting, I realized something. If the whole universe can collapse, what about smaller objects? What about individual stars? Stars are remarkably stable, for millions of years, billions even. They burn hydrogen. Fusion reactions in the core release energy. Radiation pressure pushes outward. This balances gravity trying to crush the star inward, but nothing lasts forever. Eventually, the fuel runs out. Hydrogen is exhausted. Fusion slows, then stops. The outward pressure disappears, and gravity wins. For small stars, stars like our Sun, this is relatively gentle. The star cools, contracts, becomes a white dwarf, an Earth-sized ember made of compressed matter. Hot at first, but cooling over trillions of years, eventually becoming a cold, dark sphere, a stellar corpse. But for massive stars, something different happens, something violent. When fusion stops in a massive star, the collapse is catastrophic. The core implodes in seconds. Electrons are squeezed into protons. They combine, forming neutrons. The core becomes a neutron star, a ball of pure nuclear matter, the size of a city, but with the mass of the sun. The density is beyond comprehension. A teaspoon of neutron star matter weighs as much as a mountain. That's about 1 billion tons in a teaspoon. Gravity at the surface is so strong that if you dropped something from 1 meter up, about 3 feet, it would hit the surface at a significant fraction of the speed of light. But neutron stars have a limit. About 1.5 solar masses, the Chandrasekhar limit. They can only support that much. Push beyond that limit, and even neutron pressure can't hold the star up. Then what? The collapse continues. And this is where things get really strange. So stars can collapse. But how far can they collapse? What's the limit? Is there a point where something strange happens? Let's ask the mathematics. Einstein's equations of general relativity describe how gravity warps spacetime. For normal objects, planets, stars, even neutron stars, the equations work fine. They predict how gravity behaves, how time flows, how space curves. But when you squeeze matter beyond a certain density, something odd appears in the math. A critical size? A boundary? For any given mass, there's a size below which the equations predict something bizarre. A point where the mathematics says time stops. Where space curves back on itself completely. We call this the Schwarzschild radius, named after Karl Schwarzschild, who found this solution to Einstein's equations back in 1916. Just a few months after Einstein published general relativity, Schwarzschild, serving on the Russian front in World War I, solved the equations exactly for a spherical mass. And he found this critical radius. For the Sun, this critical size is about 3 kilometers across, roughly 2 miles. For Earth, it's about 9 millimeters, about 1/3 of an inch, the size of a marble. For any object, you can calculate this critical radius. It depends only on the mass. The more mass, the larger the critical radius. But here's the thing. The critical radius grows slower than the actual radius of the object. So normal objects, stars, planets, are nowhere near this limit. Their actual size is much, much larger than their critical radius. The Sun's radius is about 700,000 kilometers. Its Schwarzschild radius? 3 kilometers. It would have to shrink by a factor of more than 200,000. But if you could somehow squeeze the Sun down to 3 kilometers across, or Earth down to a marble, you'd hit this boundary, this critical circumference where the math stops making sense in the usual way, where something very strange happens. An object compressed below its Schwarzschild radius, a collapsed star. That's what we called these things in the mid-1960s. Some people also said frozen star for reasons that will become clear, or black star because no light escapes from them. Whatever you called it, the predictions were bizarre. And the strangest prediction? What happens to someone who falls into one? Let me describe a thought experiment. Forget the mathematics for a moment. Just imagine this scenario. A massive star is collapsing. Its core is imploding. Gravity is crushing it smaller and smaller. And imagine someone, an observer, standing on the surface of this collapsing star, riding it down, falling inward with it. Now imagine you're far away, safe, watching through a telescope. What do you see? At first, nothing unusual. The star shrinks, gets smaller, denser. The observer on the surface falls inward. Light from the surface travels to your telescope. You see them there. Maybe they're waving, dancing, sending light signals. But as the star approaches the critical size, the Schwarzschild radius, something strange starts happening. The light reaching you from the surface changes. It gets redder, dimmer. This is gravitational redshift. Light climbing out of a strong gravitational field loses energy. Its wavelength stretches. It shifts toward red. The stronger the gravity, the more the light is redshifted. And as the star approaches the critical radius, the gravitational redshift becomes extreme. But that's not all. Time itself is affected. The observer's movements appear to slow down. They wave their arm. But from your perspective far away, the motion takes longer than it should. And longer, and longer. To them, nothing is different. They're waving at normal speed. Their watch ticks normally. But the light carrying that information to you is being stretched by gravity. Delayed. As the star gets closer and closer to the critical size, the effects become more extreme. The observer moves slower and slower from your perspective. Their light gets redder and redder, dimmer and dimmer. Finally, as the star reaches the Schwarzschild radius, something impossible happens. From your perspective, the observer stops, completely, freezes in place, like a photograph. Their image is stuck there at the boundary, forever falling, but never quite crossing. Time has stopped for them, at least from your point of view. Their light is so redshifted, it's essentially invisible. They're frozen at the edge of this collapsed star for all eternity. This is why some people call it a frozen star. From the outside looking in, nothing can ever cross that boundary. Everything just slows down and freezes there. But here's the really mind-bending part. What about the observer's perspective? What do they experience? Nothing. Nothing at all. From their point of view, time passes normally. They don't slow down. They don't see anything unusual. The critical boundary, the Schwarzschild radius, they pass right through it. No warning, no sign, no jolt or discontinuity. Just smooth, continuous motion inward. To them, it takes maybe a few seconds, a minute, some finite time. They cross the boundary without even noticing. But once they've crossed, something has changed. They try to send a signal out, a radio transmission, a light beam, anything, and it doesn't work. Not because the signal is blocked, but because space itself is so curved near the collapsed star that every direction is inward. There is no outward anymore. All paths, every possible trajectory, lead deeper into the star. Toward the center, they're trapped. Can't communicate, can't escape, can't signal for help. And from their perspective, they just keep falling. Eventually reaching the center, where tidal forces become infinite and everything is crushed. The math breaks down there. We don't know what really happens. From outside, you see them frozen forever at the boundary. From inside, they fell through in finite time and are doomed. Both descriptions are true. They're just two different perspectives on the same physical reality. Because time itself flows differently in different places. Near strong gravity, time runs slower relative to distant observers. And at the Schwarzschild radius, from an outside perspective, time essentially stops. This is the frozen star paradox. Two realities, both correct, both happening simultaneously. This might sound like science fiction, but it's not. Time dilation is real, measured, proven. Your head ages faster than your feet. Over your lifetime, about 90 billionth of a second faster. Tiny, but real, measurable with atomic clocks. In 1960, Two physicists named Pound and Rebka dropped a photon down a tower, 24 meters, about 79 feet. They measured its frequency at the bottom. The frequency had changed, exactly as Einstein predicted. Gravity affects time. Not a lot over 24 meters, but measurably. Earth's core is about 2 days younger than the surface. After 4 billion years, the time difference adds up. The core has experienced less time because gravity is stronger there. Near a neutron star, the effect is huge. An hour there might equal 2 hours far away. Clocks run measurably slower in strong gravity. Near the Schwarzschild radius, an hour might equal billions of years for a distant observer. Now here's where it gets personal. Imagine you watch a friend fall toward a black hole. You see them slow down, moving slower and slower, their clock slowing, every motion taking longer from your perspective. They wave. The wave takes seconds, then minutes, then hours. They freeze at the edge. Forever. You never see them cross. From your perspective, they're stuck there, frozen. Time has stopped for them. But from their perspective, they fall right through in seconds. Nothing unusual. No barrier, no warning, just smooth motion inward. Both perspectives are real. Both happening. You see them frozen forever. They experience falling through and being crushed. Both true. Remember Interstellar? Cooper falling into Gargantua, time passing differently on Miller's planet. 1 hour there equals 7 years on the ship. That's not Hollywood magic. That's measured physics. Your GPS satellite has to account for this. Clocks up there run slightly faster than clocks on Earth, about 38 microseconds per day. Why? Because they're farther from Earth's center. Gravity is weaker. Time flows faster. If we ignored Einstein's equations, your GPS would be off by kilometers within a day. Your phone would tell you you're in the wrong city. We engineer this correction into every GPS satellite, every single day. Same principle that makes your friend freeze at the black hole's edge. Just different scale. This isn't theory. This is how reality works. Time flows differently in different places. Near mass, time slows. Far from mass, time speeds up. Measurable, repeatable, undeniable. Collapsed stars don't emit light. They're dark, black holes in space. So how do we find them? Method 1. Binary systems. Look for binary systems. A visible star orbiting nothing. Empty space. The visible star moves, orbits. Something is pulling on it. From the visible star's motion, calculate the mass of the unseen companion. If that mass is beyond the Chandrasekhar limit, about 1.4 solar masses, and it's dark, it's a collapsed star, a black hole. Cygnus X1. First black hole candidate found this way. 1964. A blue supergiant orbiting something invisible, something massive. Method 2. Gravitational lensing light bends near massive objects. A collapsed star acts as a gravitational lens. If perfectly aligned, you might see a ring of light. Einstein ring. Light from a background star bent around the collapsed star requires perfect alignment. Improbable, but possible, and we've observed it. But here's what changed everything. LIGO 2015. We heard them September 14th, 2015. LIGO, Laser Interferometer Gravitational Wave Observatory, detected something extraordinary. 2 black holes colliding, 1.3 billion light-years away, space itself rippling, compressing, stretching. The wave passed through Earth. We felt it, measured it, not seeing them with light, seeing them with gravity, with the fabric of space-time itself vibrating. Think about what that means. 2 objects, each about 30 times the sun's mass, spiraling together, faster and faster. In the final tenth of a second, they merged, released more energy than all the stars in the observable universe combined, for that brief instant, but released as gravitational waves, not light. Space itself ringing like a bell, and we detected it. First direct proof these objects exist. EHT 2019. We saw the shadow April 10th, 2019. The Event Horizon Telescope captured the first image of a black hole, M87, center of a galaxy 55 million light-years away, 6.5 billion times the sun's mass. You can see the image, the shadow, the ring of light bent around it. The event horizon, the boundary, is there. Dark. Nothing escapes. But the light around it, from the accretion disk, glows. The black hole itself is about 40 billion kilometers across, roughly 25 billion miles, larger than our entire solar system. We can detect them now, not with light, because no light escapes, with gravity's fingerprints, with the warping of space-time itself. We detected this in your lifetime. LIGO 2015, EHT 2019, within the last decade. Things that seemed impossible when I was young, we've measured them, photographed them, heard them. The universe keeps surprising us, so we can find them. We've detected them. But in the mid-1960s, when I was thinking about this, colleagues had some unsatisfying theories. One popular theory said that stars simply can't collapse below the Schwarzschild radius. They can't become these frozen stars or black holes. There must be some mechanism that prevents it. The argument went like this: if a star exceeds the Chandrasekhar limit, it will do something to avoid collapsing completely. It will explode, throw off mass in a supernova, anything to get below the limit. Because if it didn't, it would keep collapsing past the Schwarzschild radius, and nobody wanted to think about where that led. But this bothered me, because it doesn't explain why stars explode. It's just saying they explode because they have to avoid collapsing. That's circular reasoning. It's like saying God causes supernovas so we don't have to worry about collapsed stars. That's not physics. That's avoiding the question. Another attitude, I jokingly called it the all right Jack theory, went like this: I can't see inside the Schwarzschild radius. I can't predict what happens there. The math breaks down at the singularity. So why should I worry about it? As long as I'm safe out here. All right, Jack. This really bothered me, because the observer falling in has a real problem, a real future, a real fate. Just because we can't see it from outside doesn't mean it's not real. It doesn't mean we should ignore it. The question of what happens inside is tricky, very tricky. The math is difficult. Our physical intuition fails. But running away from the question isn't the answer. This argument sort of beats around the bush by not answering anything. If physics predicts something strange, something uncomfortable, we don't get to ignore it just because it's inconvenient. We have to think about it, work through it, try to understand it, even if the answers are strange, even if they're unsettling. That's what physics is about. The question is tricky, and it does need some thought. Think about what's happening right now. Somewhere in space, a massive star is collapsing, running out of fuel, gravity crushing it smaller and smaller. And if it's massive enough, if it exceeds that critical limit, it won't stop. It'll keep collapsing, past the Schwarzschild radius, past the point where even light can't escape. From far away, someone watching sees it slow down, freeze. The star appears to stop at the boundary, frozen there forever. Time itself has stopped from their perspective. But an observer on that star? They experience nothing unusual. They cross the boundary in seconds, minutes, normal time, then try to signal out and can't. They're trapped. Space itself has curved so completely that every direction leads inward. Both observers are right. Time really does flow differently for them. This isn't philosophy, it's measurement. The Pound-Rebka experiment proved it. Drop a photon 24 meters and its frequency changes. Your head ages faster than your feet. Earth's core is about 2 days younger than its surface. Everybody knows time flows, but you have to stop and think about it to really grasp what that means. Time isn't the same everywhere. It bends, stretches. Near strong gravity, it can slow to almost nothing. And space. Space is expanding right now. Galaxies racing apart. We can measure it. See it in the redshift of distant light. Run time backward and everything collapses to a point. The Big Bang. Run it forward and maybe space expands forever. Stars die one by one. In 100 trillion years, the last star burns out. Then darkness, forever. Or maybe it all collapses back someday. Big crunch. Everything crushed back into a single point. We don't know yet. Individual stars collapse. Maybe the whole universe collapses, or expands forever. The mathematics predicts all of this. Strange things, uncomfortable things. But the math doesn't care about comfort. It just describes what is. Some people want to avoid these questions, say stars can't collapse that far, must explode first, or say we shouldn't worry about what happens inside because we can't see it. But that's not physics. That's running away. The question is tricky. The math is difficult. Our intuition fails. But the answer, whatever it is real. The observer falling in has a real fate. Time really does stop from one perspective while continuing from another. These aren't contradictions. They're both true. That's the inconceivable nature of it. Space expands, time bends, stars collapse into darkness, and we're only beginning to understand what it means. When you really think about it, really stop and consider what the equations are saying. The universe is far stranger than it appears. Not simpler, but more strange. And understanding that strangeness, really understanding it, that's what physics is. If this changed how you see the cosmos, even a little bit, let me know in the comments. What clicked for you? What still feels unsettling? Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.